Welcome to the second week of the lecture on our subject BFM3303, electrical drive system. So this week what we're going to do is basically we are going to start to look at the notion of magnetic circuits. We will learn how is a magnetic circuit constructed and what are the basic assumptions behind the construction of a magnetic circuits. Okay, so if we look at a bit revise what we have seen last week, we have basically seen the revision on electromagnetism, basic principle of electromagnetism. So we have looked at terms that we are going to frequently encounter through this subject, basically especially in the first part of electrical machines, which were we have looked at the difference between magnetic field and magnetic force, because they are not the same thing. And then we have looked at what is magnetic flux. So magnetic flux basically it is related to, if you remember, to a selected surface area where magnetic field B can also be seen as what we call magnetic flux density, right? And then we also look at very quickly into basically the origin of those magnetic forces. So current conducting conductors, current conducting wires, or permanent magnet. And at the end, we have basically tried out some exercises related to those terms and basic principle notions. Okay, so this week what we're going to do is we are going to take from the basic principle notion of electromagnetism. We'll try to construct what we call a magnetic circuit. So what we mean by magnetic circuit is that we will have somehow, like in electrical circuit, a certain source that produces that magnetic flux, and then that magnetic flux will circulate in a certain circuit which will be defined, and then there are certain parameters that can be deduced from that circuit, just like in electrical circuit. So let's begin. So last week we have looked a bit at the notion of the introduction to the notion of basically a current circulating inside a winding that is enrolled around a core material that is that form a closed path like this. So we learn basically inside this kind of circuit, when you have a current source that's applying current to your winding, to your coil, that is forming a closed contour, what we call as closed contour. We have basically several equations that can explain the behavior, electromagnetic behavior inside the this component. So we have the first one, what we call as MMF, or magnetomotive force, is equals to the product of the number of turns. So N represent the number of turns of how much turns of winding that you have around your core material, multiplied by the intensity of the current that is circulated in that windings. So that's what we call as magnetomotive force. So in simple words, it is similar, quite similar. I mean, it is analogous to EMF in electrical, electromotive force. So magnetomotive force is basically the force that is necessary to push the magnetic flux to circulate inside this toroid. Okay, so from there we know that if you have current circulating inside your conductor, you will have a magnetic field inside it. So that magnetic field is what we call as H, right? And H is what we call as excitation magnetic field. So H, what is it equals to? It is equals to what we call as H is basically in this circuit, it equals to the MMF divided by L. So it depends, the H depends inside the toroid. It depends on the total length of the core material. So it's, as you can see, if the length is smaller, then you get a higher excitation magnetic field excitation. So what does it mean to have a smaller L? A smaller L means the radius of your core over here would be much smaller. If the radius of the core would be much smaller, then it means that at the same number of turns, you'll have your winding will be closer to each other. So if you have your winding tighter and closer to each other, you basically create a higher magnetic field excitation. So that is H equals to the magnetomotive force MMF divided by L. And then of course there is not just the magnetic field inside the coil. The magnetic field inside the coil will circulate in the core material that we can see over here, right? So the core material, the magnetic field inside the core material, we call it as B. And B in relation to H, basically it is proportional with a constant of mu. So B equals to mu H. What is mu? As we mentioned last time, mu is basically the permeability of the material. So in this case, it is the core. So if you have a high mu, then you have a higher magnetic field inside the core, but you have a smaller mu, then you have a less intense magnetic field inside the core. So imagine if you don't have any core material, then the excitation, the magnetic field inside it will be just H. And then of course there's relation with what we call flux. So it's easier to think of magnetic circuit in terms of flux. So as we have seen together last time, if the line that we are seeing in magnetism visualization is basically what we call field lines. Field lines also can be considered or can be seen as the flux. So it is the circulation of that magnetic field, right? So flux in relation to magnetic field is basically magnetic field B equals to a flux divided by the surface area in which the flux circulate, the magnetic flux circulate. So imagine if you have so this core material, if you cut through it, if it has a larger cross section A, then it means the magnetic field inside that core will be lower. But if if the cross section A is smaller, then the magnetic field B will be higher. Of course, the increase of B with the decrease of A will not be continuous forever. There will be a limit, what we call saturation. So this relation of B equals to mu H, there is a saturation limit that we will probably discuss later, but for the moment we can take this as equation. So you can see from the third equation, basically what we can explain more is basically B instead of calling it as just magnetic field inside the core, we can usually call it as flux density, because it shows us how much flux, magnetic flux. So this is the line of magnetic flux that we can see over here. How much of magnetic flux that we have per cross section, per area of core material. Okay. So in order to summarize this in a more generic form, basically in a closed magnetic circuit, called here in this example is called toroid, but it can be in another form as well, a rectangular or in any other form. In that matter, if it is a transformer, then it will be in rectangular form. If it is an electrical machine, then it will be another form, which will be much more complex. But in this case, this is what we call toroid. So in a closed magnetic circuit like toroid like this, generic equation can summarize all for any section of the toroid using these two equations. So this equation basically is generalization of the equation that we can see over here. So this equation that explains, the first equation explains magnetic field in a closed contour C. So this is basically integration in a closed contour C. Closed contour C means is this closed path C. So if you addition all the H across all the magnetic excitation across the inside of the toroid, multiply by the length. So dl means you add all the smaller length of the toroid. So the integral of dl means it is the total length. If you multiply h by l, it will be equals to the integral of j and dA. So what is j? So it is another term that we may introduce. J is basically what we call a current density. So current density means how much current you have per cross section. So it is a more generic form. It doesn't depend on the number of turns and current. We will look directly at per surface area how much current do we have. So that's what we call current density. So current density multiplied by the cross section area, it will get us basically the value of current. Right? So it's value of current. It's equals to the same thing as Ni. So this is a more generic form. And then we have the second equation that describe the phenomenon inside this as well. The second equation basically tells us that the integral in the closed contour on the closed surface S. So if we take between two surface S inside the core, the magnetic field B multiplied by the surface area A will be equals to 0. What does it mean? it simply means that the magnetic flux density, so B multiplied by A, if you look over here, it explains basically the generalization of this equation. B multiplied by A equals to flux. And it says that in a section, if we add up across the section, the flux is equals to 0, which means that the flux density in a closed surface S is conserved. Or in other words, what does it mean? Is basically, if you look at the flux from 2 points across the section, let's say we take from this section and this section over here, the flux, if we sum up, so because integral is basically the sum, right? So the sum of the flux entrance the section plus the flux that leaves the section will be equals to 0. It means that the flux or the flux density inside the core is conserved. It means anything that goes in will keep being inside the core material. It means that the flux is not leaked towards the exterior. The magnetic flux always circulate and always stays inside the core material. Okay. So from there, what we can do is basically we can do a certain simplification. So let's say now instead of having a toroid, we'll have a material that looks rectangular. So basically this is the form that we are using in a transformer, right? If you remember the electrical courses, a transformer basically is made of a core material, and then you have a winding coil with a certain number of turns in the input, and you have another one on the output. But now we're going to look at only with one winding like this, with one turn of coil. So we can simplify basically the phenomenon using the concept of magnetic circuit. So here the same thing happens. We have a certain coil with a winding with turns n turns, and then we supply it with a certain current intensity of I. So it produces a magnetic excitation, therefore there will be a magnetic flux. And because of the core material that has a higher permeability mu, then the magnetic flux will basically stay inside the core material. So you can see over here, this line represents the magnetic flux line or the magnetic field line. Okay. So let's say the core material now is in form rectangular. It has the mean core length of LC. Mean core length means if you take in the middle, you measure the length of the closed path, it will become LC. And it has a cross-sectional area of AC. So we can say that we have now a magnetic circuit where the magnetomotive force that's creating the magnetic flux is created by this coil, and we have a magnetic flux that keep on circulating inside this core material of length LC and cross-sectional AC. Okay, so the magnetic circuit is always in this form. I mean, this is the basic fundamental form of it. It will be made of a permeability structure called core. So there will be always a core because you don't want the flux to be leaked in the air. So this will cause the magnetic flux to be confined in the structure. So this is basically the core material. If we take an analogy of electrical circuit, it serves just like a conductor, right? So it serves like a conductor that confines current in the electrical circuit. So now, after having defined the essence or the basic principle, the basic component that we need in magnetic circuit, now let's look at what we can do with it. So the core, as I mentioned just now, has uniform cross section of AC made of ferromagnetic material with mu much larger than mu zero. So the purpose is not to have the magnetic flux leak towards the air. And we have magnetic excitation by a winding of N turns and current of I amps. So the winding produce a magnetic field in the core. Ni is the MMF. So Ni, if you do calculate Ni is basically what we call the MMF. So the MMF can be symbolized by F, the force of magnetomotive, right? So magnetic flux then circulates and confined inside it. So in terms of equation, you can write that MMF equal to Ni equals to, therefore, the excitation inside it, H multiplied by LC. So this is just in integral form if you want to take only a portion of it, but in general, if you're taking the whole length of it, then it will be equals to HC LC, right? But now, in rotating machines, where we will have energy conversion, we cannot just circulate magnetic flux in a closed contour. We need to basically transform it into movement. We need the magnetic flux to interact with another component that will be dynamic. So therefore, what happened in energy conversion device, electromagnetic or electromechanical conversion device, the magnetic flux usually pass between static and rotating parts. So imagine if you have a motor, what happens is you have a coil that will be fixed into a certain part that we may call as a stator core, but the magnetic flux will be also channeled into another part that will be moving, that we would call as rotor. So in order for the magnetic flux to pass from a non-moving part to a dynamic moving part, it needs what we call an air gaps, because if you have two components, let's say you have what we call a stator and a rotor in the middle, you cannot have them you cannot have friction between them in order to have continuous contact to allow the magnetic flux to circulate through it. So what you need to have is basically between two components of stator that's not moving and the rotor that will be moved, that will be rotating, you need a certain air gap, right? So it could be represented in this case an air gap like this. So it needs air gap where what happened in the air gap is basically the permeability at the air gap will be the permeability of air. So we will have a very low permeability in a small section where the magnetic flux will have to jump over it, and the permeability of this air gap will be equals to, of course, close to the permeability of space, which is mu0. So for this kind of air gap, let's say we define the parameters of air gap with a length g, which is of course smaller than the core section. It needs to be smaller in order for the flux to be able to jump over and not leak into the ambient. So the flux will, if it is small enough, smaller than the core section, then we can consider that the flux will follow the path. It will jump over the air gap and it will continue to circulate inside the core material. But the problem, if you have an air gap that is too large, what happens is now instead of jumping through the air gap and goes back inside the core material, you could create leakage where the magnetic flux just go outside and came back through the outside, through the air and not through the magnetic core. So what we want to have is basically we want to, in order to write equations related to magnetic circuit, we need all the magnetic flux lines, all the flux to be confined in that area in the core. So we need to have a smaller air gap. So in electrical machines, in motors, we have a very small air gaps, and it is a very crucial design parameters inside an electrical machine. So if we look at this, instead of having just now, what we have is we have only F magnetomotive force equal to HCLC, but now knowing that we have air gap, we will add another terms of Hg multiplied by G, right? So we don't only have Hc, which is the magnetic field inside the core multiplied by the length of the core, but now we have another section which will be the excitation, now not inside the core but inside the air gap, multiplied by the length of the air gap, Hg multiplied by G. So now our equation, this lead to a magnetic circuit equation of MMF equal to HCLC plus Hg multiplied by G, right? So if we develop further H, we know that H is basically in relation to the magnetic field inside the core, because now we have a core material. It's not just air, right? It's not just excitation. We know there is the coefficient mu that intervene, right? Because B equals to mu H, therefore H equals to B over mu. So we can rewrite our equation as MMF equals to BC, so magnetic field inside the core, divided by mu, so permeability of the core, multiplied by LC, length of the core, plus BG mu0 multiplied by G. So BG is the magnetic field inside the air gap, right? Or flux density inside the air gap, divided by mu0, so it's the permeability of air, of space, multiplied by the length of the air gap, right? So from the equation over here, what we can see is we know that from the previous equation, previous slide, we know that the relation between flux and magnetic flux density B is basically B equals to flux divided by A, right? So flux equals to B multiplied by A. So if we replace basically B by flux divided by A, so imagine you replace BC by flux divided by A, and the A will be AC. Here flux divided by A will be AG. So you'll get to this equation where you have the MMF, magnetomotive force, equals to so flux LC divided by mu AC plus flux G divided by mu 0 AG. So if you basically factorize the flux, you get flux multiplied by LC divided by mu AC plus G divided by mu 0 AG. So this particular part basically is attributed to the core material. So it's the length of the core divided by the permeability of the core multiplied by the cross section of the core. And here it is attributed to the air gap. So it is equal to the length of air gap divided by mu 0, so the permeability of air, divided by the cross section of the air gap. So this is a very interesting equation because we have here magnetomotive force, we have a flux over here, and we have a certain coefficient that is the sum of the two part, which is the core and the air gap. So the two terms in the middle that we have over here, if you look back at the equation, so here was the equation in the previous slide. These two terms is basically the two terms that multiply the flux. So this is multiplied by flux. This is also multiplied by flux. These two terms that multiply by flux is what we call as reluctance. So we have reluctance of the core. We call it as RC. Reluctance of the core, the first term over here, and the second term, the reluctance of the air gap over here, the second term. If we look at these terms of reluctance, if we try to replace it with values, we know that the reluctance of the core will be much smaller compared to the reluctance of the air. Why? Because if you look at AC and AG, the cross section, they will be more or less equals. G would be smaller compared to LC, but if you compare the mu over here is much larger than mu 0, because mu 0, if we remember the first lecture talking about permeability, mu 0 is basically the permeability of space or air. It is much smaller compared to the mu of the material of core. So it can be 100 or thousands times smaller. So that leads us to a reluctance of the core, which is much smaller because the mu is much higher, and the reluctance of the air gap will be much higher. So what does this reluctance means? Reluctance actually means it is a measure of difficulty for the flux to pass through it. Okay, so it means if you are in the core, the reluctance inside the core is very small because mu is very high. It means for a magnetic flux, to go through the core, it is easy, but for a magnetic flux to go through the air gap will be very hard. So if you have a larger air gap, that means in order for the flux to go through it, you need a higher magnetomotive force. Okay, so therefore what we can do is basically we can also write the equation as replacing if we replace basically the reluctance over here with just the term RC and RG, we can write the equation as magnetomotive force F equals to the flux multiplied by the sum of the reluctance. So this is quite particular because it is very similar to what we have in electrical circuit, right? Where we have a certain force. Here is magnetomotive force, but in electrical circuit you would have voltage, which is what we call electromotive force, and then we have flux. But we have flux in magnetic, but in current we also have a certain flux, but it is a flux of charge, and that's what we call current, right? And we have a sum of reluctance, and in electrical you have a sum of resistance. So it is very similar between electrical and magnetic circuit. We can make a circuit that use the same symbolic component of electrical, but representing a magnetic, not electrical behavior, right? So instead of having basically voltage, you'll have magnetomotive force, mmf. Instead of having current, it is flux, and instead of having resistance, you have what we call as reluctance, right? So if you want to find basically the flux is just the mmf divided by the sum of resistance. Just like in electrical, if you want to find the current, it is basically the division, it is the potential difference, the EMF, voltage divided by the sum of resistance. Okay. So now we have looked at it. It is very similar. If we write them side to side, we find that so F mmf is similar to in electrical as the EMF. So it is either electromotive or magnetomotive force. It's the same thing basically. In magnetic, because magnetism in electricity is basically just two sides of the same coin. If you have electricity, then you have magnetism. So if you have electromotive force, it is the force that you need to push charges to go through the conductor. Magnetomotive force is basically the force that you need to push the magnetic flux to circulate inside the core. Okay, and then you have which is similar, flux and current. So flux represent the flow rate of magnetic parameter, but current it represents the flow rate of charges inside your conductor. And then we have the same terms that measure the resistivity, or the measure of how hard it is to circulate that flux or current inside the circuit. So this is what we call a measure of resistance. In magnetism, in magnetic circuit, is what we call as reluctance. So what we can see from this equation, so from the circuit we can simplify it into an equivalent magnetic circuit, where we have basically the source, the mmf and I, and we have the two resistance. I'm sorry, we cannot see, it's hidden behind my video here. We have a resistance that's representing the reluctance of the core, and there will be another resistance representing the reluctance of the air gap, and you have the equation over here to calculate those reluctance, right? So this is what we are going to use in order to calculate parameters in magnetic circuit using an equivalent magnetic circuit model. So from the equation, several remarks can be done. So for example, we can see that if you have higher material permeability, so if you have a higher permeability, then this term will be smaller. So for a constant magnetomotive force, if this term is smaller, then you will allow a higher flux to circulate in it. In opposite of it, if you have a lower material permeability, then you will have a lower magnetic flux available to circulate in your magnetic circuit, right? So most of the mmf, if we look at the circuit, knowing that it is the reluctance of the air gap that is important, so most of the mmf and I that we have over here is basically used to drive the flux to go through past the air gap. So due to this analogy, basically similar law that is applied in electrical circuit that you use in electric circuit can also be applied in magnetic circuit. For example, you remember in electrical courses, you have Kirchhoff law, voltage law, and Kirchhoff current law. So in this application on magnetic circuit, we will say that the sum of mmf in a loop is 0. So the sum of if you take the mmf for the core and mmf used by the air gap, the sum of them will be equal to the mmf provided by the current supply. So this is basically the equation that I explained it. So mmf supplied will be equal to mmf consumed by the core, mmf consumed by the air gap. The same goes for current law. In electricity, in electrical, we say that at a node, the sum of current entering the node and quitting or leaving the node will be equal to 0. The same thing goes for magnetic. Sum of magnetic flux on a node is 0. So in simple, we can write it as this, as this equation. The sum of magnetic field that goes into a node will be equal to 0. So example, we take this node over here, the sum of flux that goes into this node. So there is a flux that coming from the core goes into this node, and there is the flux that goes out into the air gap from this node. The sum of them will be equals to 0. So after this, if we are treating exercises or problems related to magnetic, we can use the same principle in order to find out different parameters of our magnetic circuit. So there are several remarks that we have to make regarding the theoretical part that we have laid out just now. So in practical, just now we said that the cross section of the core and the cross section of the air gap would be equal, could be considered as equal. But if you look closely, basically usually the flux that goes through the air gap are not in straight lines. They create what we call as fringing fields. The fields tends to basically jump before they arrive at the cross section, jump through the air. So if you look at the surface area that the flux takes, or the magnetic field takes in the air gap, it is much larger. But this fringing field is very minimum is if the air gap is quite small. So in principle, if there is no the difference would be just there will be uncertainty or small error due to the calculation of the surface area A of the air gap. But nonetheless, all the magnetic flux, if it is small enough and all the magnetic flux still goes through the core, then the principle of magnetic circuit is still valid because all the flux still circulate in the core. So however, if the fringing field fringing field can affect the calculation of reluctance, because as I mentioned just now, the air gap could be much larger. So that means that when we create an electrical machine, the air gap cannot be too large. So it needs to be as small as possible so that no magnetic flux leakage are created. Okay. And then the second thing, this is another term that we can introduce. So the measure of flux per amount of current supplied. So we know MMF is N multiplied by I, and that I will create a certain flux, right, inside the core and inside the air gap. The measure of flux per amount of current supplied is what we call inductance. So you may have heard of inductance. We have basically learned it in electrical courses, where we use it basically to regulate fluctuation of current. So that inductance is basically the measurement of how much flux is created per current supplied to the core material. Okay, so flux divided by I is what we call inductance, and is measured in Henry. So we can see that a machine, or this is an example of a toroid inductor that used in electrical circuit even. So the inductance will be much larger if you have higher flux, and in order to create that higher flux, of course, at a constant, we are considering at a constant current I. If you want to create a much higher flux, what you need to do is basically to it will be depending on the core material. If you use a mu that is higher, then you create a higher inductance. And we also depends on the basically the length of the core. If it is much tighter, then the inductance will be high as well. So this inductance is basically an important measurement that we'll see later in the theory of electrical machine, and is also used in inductor for electrical and electronic circuits. So that's all about it. That's all about basically the basic of magnetic circuit. So we have those introduction to magnetic circuit is very useful for us to introduce the notion basically of MMF, inductance, flux leakage, because they are the things that we're going to use and apply in the design of electrical machine, because we're going to look at different type of electrical machines. But for now, what we can do regarding the knowledge that we have now regarding magnetic circuit is that we can do several exercises. So there are 2 exercises in the slide that I provide inside your Google Classroom. Please try first on your own. You can try it on your own first, and then later we'll do correction during a tutorial session. So this first one is basically the same circuit that we have been using in the lecture. It's just that now certain parameters are given, and you are asked basically to calculate certain things, right? So for example, here it is asked to find the flux and the current I following a certain parameters that were given. And here it is more in the form that is closer to applied electrical machine, where we have basically the MMF that is supplied to what the structure that we call rotor. Now it's not in the form of a rectangular form with air gap. Now we have a core that is becoming a rotor, and we have basically another material which is the core on the outer side, which we will call as stator, and the magnetic flux will basically circulate from the rotor to the stator and goes back into the rotor. So we have two air gaps over here. So there will be certain calculation that will be interesting for you to try out, and I will explain it more in tutorial session, or the correction of the tutorial will be given for you later. Okay, so thank you for now. I'll see you next week. In the next lecture it will be something that will be introduction to induction machine. Thank you. See you next week. Bye.